In this last section of thermodynamics, we want to investigate whether or not a reaction will occur. And we know that in nature some reactions occur naturally while others do not. And so we'll look at what factors play a role in determining whether or not a reaction will occur. A reaction that occurs naturally is known as a thermodynamically favored process, and we'll abbreviate that TFP. In your textbook, you may see this called spontaneous. Let's see if I can type that out for you. Spontaneous. Now, AP Chemistry wants to move away from the use of this term because most of the time when people think of spontaneous, they think of fast. And we want to make sure we differentiate here. When we say that a process is thermodynamically favored or even spontaneous, to use the term in your book, we're not saying that it's fast. We're just saying that it proceeds without any assistance from outside the system. For example, if you have water sitting at room temperature, some of it will evaporate. You don't have to do anything to the water to get this to occur. It is a favored process. If you have iron in the presence of oxygen and water, it will rust. Now that may not happen immediately or even over a year, but it will happen without any assistance from outside the system. And if you put salt in water, it will dissolve. Even if you don't stir it, over time it will dissolve. And so we're looking at processes that happen naturally or spontaneously. These processes are known as favored. Let's look at some examples of some processes that aren't favored. So, let's see if we can go back up here. A non-thermodynamically favored process is a process where assistance from outside is necessary in order to induce the change that you want. For example, if you have water at 75 degrees Celsius and you want it to boil, it's not going to happen. No matter how long it sits there at 75 degrees Celsius and normal pressure, it will not boil. You're going to have to do something to the system, and in that case, you need to heat it up. Or you could change the pressure. Again, water does not freeze at 15 degrees Celsius, no matter how long it sits there. In order to get this to happen, you're going to have to change the system. Another example is the reaction that you see at the bottom. And that reaction is iron oxide, which is rust, does not react with carbon naturally to form iron and carbon monoxide. What that's saying is rust is not going to undo itself naturally. We saw that rust will naturally form, but the undoing of rusting to change it back to iron is not a favored process. That's going to require energy. If you have a process that is favored in one direction, then it must be non-favored in the reverse direction. For example, water liquid changing to water solid, also known as freezing. If you're at negative 10 degrees Celsius, that is a favored process. It will happen. However, water solid will not change into water liquid at that temperature. You'll notice as we go through these examples that temperature plays a key role, because a process that is not thermodynamically favored at one temperature may be favorable at another. For example, water changing from solid to liquid is not favorable at negative 10, but it would be favorable at positive 10. So we'll keep temperature in mind as we look at these examples. What decides if a process is thermodynamically favored or not? One factor, and this is only one factor, but it is whether the process is exothermic or endothermic. So remember we talked about delta H in the past two lessons. So when we say that the process is exothermic, we're saying that the delta H value is negative and that heat is being released. These processes are often favorable because nature favors a reduction in energy. So if you'll remember, if it's exothermic, then our energy plot would look like this, where we're going up, breaking the bonds, coming down, making the bonds, and if it's exothermic, we're going to land down here at this lower energy. In these processes, the bonds in the products that we're making, they're at a lower energy than the bonds in the reactants were. And remember, that also means that they're either stronger bonds or maybe there's more of them. The difference in these two energies is released as heat. So in general, nature prefers thermodynamically favored processes that are exothermic, but that's not always the case. For example, evaporation, the changing of water liquid to water gas, is an endothermic process. It has to pull heat from the surroundings to do that, which is why your skin cools off when your sweat evaporates, because that evaporation pulls the heat from your skin. Another example is the evaporation of C3H8. It also is endothermic. And you'll see they have different delta H values, but they're both positive. However, these processes do occur at some temperatures, and they occur favorably. So the delta H value is not the only component that decides if something is thermodynamically favored or not. Another example of an endothermic reaction that's favorable is the dissolving of salt in water. Sodium chloride dissolving in water actually requires a little bit of heat from the surroundings, but it's still a favorable process. So we cannot solely use delta H to tell us whether something is favorable or not. We must also consider something else called the entropy. Now, entropy is a measure of the disorder of a system. Think of it as a measure of the randomness of the system. A greater degree of randomness or disorder is favorable, and a positive value for delta S is favorable when we're talking about thermodynamically favorable processes. To find delta S, you simply use the S value of the products minus the S value of the reactants. We are not commonly going to calculate delta S. Instead, we want to be able to tell if it's positive or if it's negative, if we're creating a greater degree of disorder or a lesser degree. Here are some examples that have a positive entropy, and they show us that an increase in entropy or an increase in disorder is a natural process. Your house naturally gets dirty. It does not naturally get clean. That is an increase in disorder. When you make a stir fry and you got the broccoli and the broccoli doesn't all gather to one side and the carrots to one side naturally. They mix. They have a lot of randomness naturally. If you wanted to take out the carrots because your brother doesn't like them, that would require energy. If you think about maintaining your lawn, you've got the weeds, you've got the grass growing, you've got the leaves falling on it, you've got the ant hills, in our case, constantly mounding. It's impossible to maintain a perfect lawn. It requires energy because nature, which our lawn is, even though we try to act like it's part of our house sometimes, it's nature. It tends toward randomness. If you spill a glass of milk, you knock it over, it doesn't stay in the cup. It goes where there's more randomness. It can spread out all over the table. You break a window, it doesn't come back together on its own, right, in a nice orderly fashion. It shatters into 1,000 pieces. Nature favors disorder, and to create order requires energy. So when you think about that, when you think about the fact that all around us we see so much chaos, but then if we hone in, we also see such beauty and such order. For example, in the way a tree has these specifically shaped leaves, or the way that the universe is put together, right? We have just the amount of gravity that we need, and we have our plants producing the oxygen that we need at the right levels, etc., etc. It kind of points to something greater. If all around us there's disorder, then we know that order must come from something because it requires so much energy to create order. Alright, moving on, we have two laws of thermodynamics. One is that the energy within the universe is constant, and we had talked about this previously. If something is increasing in heat, the heat had to come from somewhere. And if something decreases in energy, then that energy has to go somewhere. So energy is just constantly moving. But entropy is not like that. Entropy is not like an entity, like heat. Entropy is just the disorder around us. And the second law says that the disorder of the universe is constantly increasing. And so for a process to naturally occur, it must increase the disorder of the entire universe. So the order within a system could actually, it could get more ordered, but it's going to require the total disorder of the universe to increase. And we'll look at that more specifically. So two laws: energy cannot be created or destroyed, it's constant, and then entropy is always increasing. All right, let's look at delta S just a bit more. Here we're going to look at some processes where delta S is positive or negative. So in these processes, delta S is positive. That means that the disorder is increasing. And you would be asked to predict whether disorder was positive or negative for certain processes. So for these, it's positive. Something melting, going from a solid, where there's a lot of order, to a liquid where there's less order. So the disorder is increasing. Vaporization, going from a liquid where there's some order to a gas where there's really no order. So disorder increasing. Reactions where the products have more particles than the reactants. So let's say you're doing some reaction and you have 4 moles on the left, but you have 6 moles on the right. And we'll look at an example. That's going to create more randomness, more disorder. Most of the time when we make a solution, we're mixing two things together. That's going to increase the randomness. We'll see one exception to that. When we add heat, it's going to make particles move faster. That's going to create more randomness, a positive delta S there. And if we increase the volume of a gas, we give it more space to spread out, move around, there's more places that it can move to, more randomness, positive delta S. So here's some pictures kind of describing those processes that we just spoke about. Here's melting, solid, very organized, liquid, less organized. So we increase our S value. So our change in S is positive. Vaporizing, we have liquid with some order, gas, almost no order, so huge change in disorder, or S. Here we have a reaction where we have a liquid going into a gas, so that automatically is an increase in disorder, regardless of the number of molecules. You have a liquid going to a gas, so pay attention to your states when you're wondering if it's an increase or a decrease in disorder. Liquid to gas, that's an increase. We also here, though, have 4 moles on our reactant side, and then if you add up your coefficients, you've actually got 29 moles or 29 molecules on the product side. So that's a huge increase in the number of potential ways that this can be arranged, and so that is an increase in delta S, or a positive delta S. Most of the time when we make a solution and we're using solids and liquids, we're going to go from something that was a little more organized, maybe even really organized, like in a salt, like you see that ionic lattice at the top, and then when we mix them, we increase the number of ways it could be arranged, and so there we have a positive delta S. Now when we talk about the disorder of something, even an ionic solid has some disorder because those those particles can move within that structure. So there's really nothing that has no disorder. We're just looking at the change. Is it increasing its disorder through this process or decreasing? And if you're going from a structured lattice to a liquid that you're dissolved in, you're increasing your disorder. So that would be a positive change. The exception here is if you have a gas and you make a solution with it. So a gas has tons of entropy in itself because those molecules are moving fast and really randomly. And if you take that gas and then try to shove it into a liquid like you would in a carbonated beverage, you are decreasing the entropy of those molecules. They don't have as many options as to where they can go. So that would be a negative delta S. Whenever we add heat to something, we're increasing the delta S value. And you see here This is an interesting graph. We have entropy on our y and temperature on the x. So you see that there's a direct relationship. As the temperature goes up, so does the entropy. However, when we do a phase change, the temperature stays the same, but the entropy shoots up. For example, when you melt a piece of ice, that piece of ice will stay at the exact same temperature until it's done melting, but as it melts, its entropy goes up, even though its temperature stays the same. The same thing for boiling. When you boil a substance, it stays at the same temperature. This is kind of mind-boggling at first, but if you put a thermometer in the pot of water next time you boil it on the stove, the temperature will go up and up and up and up, and once it comes to a boil, the temperature is going to stay the same, no matter, how long it boils. Until it boils dry, the temperature will stay the same. But notice that entropy increase for boiling is much greater than it is for melting. We're going to change the entropy a lot more from a liquid to a gas than we will from a solid to a liquid. If we go the opposite way, like gas to liquid or liquid to solid, then our delta S values would be negative. Ooh, here's that old Boltzmann distribution plot again. This is showing us, remember, the change in kinetic energy as we add heat, and our particles stay the same, but they just become more spread out in terms of number. So here at the lower temperature, our particles are kind of concentrated in this energy range. But when the temperature goes up, they're more spread out in terms of their energy. So that higher distribution of kinetic energy means that our delta S value will increase or be positive. This is the explanation for what we saw on the last slide. So why does the entropy go up when the temperature increases? Because we have a greater distribution of kinetic energy. If we increase the volume, we give those particles more room to spread out, and so that's going to be a positive delta S as well. On the flip side, if we decrease the volume, of course, the delta S would be negative. So again, how do we calculate delta S? What if we want a number for this? We're going to use that same equation that we use for the delta H formation values. We're going to do the sum of the products minus the sum of the reactants. These values, again, are going to come from a table, so you would look them up for all the molecules. However, unlike delta H, no molecule, no element, even if it's in its standard state, is going to have an entropy value of 0. Nothing does that unless it's at 0 Kelvin. And remember, that is never been reached before. So every molecule on Earth has some entropy. It has some movement to it, some randomness to it. So if we wanted to calculate delta S for this process at 298, that's standard temperature, 25 degrees Celsius, we would look up the value for N2O4, that's our product, minus the value for O2 times 2, because it's our reactant, and N2 times 1. So products minus reactants, and remember your coefficients. I'm just going to put this up here. Again, you would look up these values in some table. You would not be expected to memorize or anything like that. So the only thing you need to remember is to use your coefficients and to do products minus reactants. We do need to pay close attention to the units though, because the units for delta S are different from the units for delta H. These are the units for delta S. Joules, not kilojoules, per Kelvin is based on temperature, so Kelvin goes on the bottom, times moles. So it's similar, we have the energy per mole, but we also have this temperature component that we didn't have with delta H. And we have joules instead of kilojoules. Alright, we'll stop there talking about delta S, and we'll pick up next time on how can we tell, we'll go back to that main question, how can we tell if a process is thermodynamically favored or not?